Okay, here we go, Zach. This is lesson number 68. It starts on page 276 of your book, and we're going to go over more about complex fractions. So this should be a pretty straightforward one because it's just taking what you already know to the next level and applying it to more complicated fractions, like fractions on top of fractions type of thing. Okay, let's look at this comic first, though, because look, it's so funny. The firefighter is saying, "Now calm down there, ma'am. Your cat's gonna be fine, just fine." Because obviously this lady is very excited to get the cat down from the tree. So, anyway, okay, pretty funny. All right, so let's jump into the lesson. So it talks about how in lesson 61, we already defined what it means to be a rational number. And remember, rational has the word ratio in it. So anything that can be expressed as a fraction is a rational number. So these are all rational numbers. So this first one is a rational number, 13, because it can be expressed as 13 over 1, right? So yeah, we could do that pretty easy. The next one, 4 over 7, that's obviously a ratio, so that's a rational number. Negative 5 over 14th, nothing says that a ratio can't be negative, right? So we can have a negative rational number, that's fine, it's still rational. Same with negative 6 over 13. And then this is a mixed number, 2 and 1/3, but it could also be expressed as 7 over 3, right? You can turn a mixed number into an improper fraction, so that's fine. That still counts as a rational number. So those are all rational numbers. Okay, got that? Yes, got it. George Costanza has it, so we'll move on. Okay, the next thing to go over is what about a rational expression? Now, this is a new term for us, rational expression. So it's basically just an expression that has variables in fractional form. So a rational expression can be any of the ones above. It does include things like 1 over 4, just like all those things we talked about before. But if it's 1 over 4x, now it's not a rational number, it's just a rational expression, right? Because we've started to incorporate variables into it. So now something like this has sort of increased in complexity, and we'll call it a rational expression instead of a rational number. Rational expression is more accurate. But 1 over 4 just by itself, even without the x, is still a rational expression, right? Because that x could be 1. So rational expression is a more inclusive term. It includes all the rational numbers, but it also includes things with variables. So let's go over some examples. This is a rational expression right here, x plus y over 4. It has variables. It's written as a ratio. That's fine. It's a rational expression. It includes rational numbers and rational and variables, okay? What about this one? It's basically the same thing. There's a negative sign, but that's fine. We learned that rational numbers can be negative, so that's totally fine. What about this number 5, just the 5 by itself? Is that a rational expression? Well, sure, because it could be 5 over 1, and that's a rational number, and all rational numbers are also part of rational expressions, so that's fine. That counts. What about this one? Yes, I mean, this is what I actually think of in my head when I hear the word rational expression. It's a ratio. It has numbers and variables in it. So, yes. And then this one, this is also a rational expression. So, rational expression is sort of a catch-all term. It has ratios in it. It has variables. It can have numbers. And that's what it means. Okay, now, one other quick review. This is important too. The denominators in all of those rational expressions, like if it's 5 over x, it's understood that the x is not 0 because you can't divide by 0. So that's going to be sort of assumed in all of these problems that since you cannot divide by 0, not allowed, you have to eliminate or omit all the, anything that makes it equal to 0. That's a no-go on the bottom. See, this is what happens when you divide by 0. Go ahead, divide by 0. See if I care. All right, so can't do that. All righty. Now, this one's the review that I was getting to. We're going to add rational expressions with the de Nuesquisser rule. Remember the de Nuesquisser rule? It's the denominator, numerator, same quantity rule. I know you know it because you've been doing it in all of your homework. You just maybe don't remember that name of the de Nuesquisser rule, but it's the denominator, numerator, same quantity rule. And what it means is you find a common denominator. So let's say you are trying to add these two things, a over b plus x over y. Of course, you can't add them until you get a common denominator. So we're going to say the common denominator is by. And then we're going to multiply the first expression by y over y. And we're going to multiply the second expression by b over b. And that's the denominator, numerator, same quantity rule, because you're doing the same thing to the bottom denominator and the top numerator, and you have the same quantity. You're not changing the value of anything. But now you have something that you can add, because this is going to turn into ay here and bx here. And now you can add these because you're going to have a by on the bottom, and on the top you're going to have ay plus bx. Okay, so now they're added. That's it. So that was just a quick review on the de Nuesquisser rule. And the other thing is we're going to use this same rule to help us simplify fractions of rational expressions. So these are complex fractions. So we're going to use the de Nuesquisser rule to simplify fractions. So let's say we have something like this. And this whole thing is the numerator, and this whole thing is the denominator. So we have x over y divided by b over c. What I think about when I solve a problem like this is whenever you divide by a fraction, you multiply by its inverse. So I have x over y on the top. This part, dividing by this, is kind of like dividing by this fraction. And in order to divide by a fraction, I multiply by that fraction's inverse. And then once you multiply by the inverse, you can just multiply straight across. So I have xc on top, yb on the bottom. Okay, so that is the short and easy way to do it, and that's how I do it, and that's how I remember how to do it. But the de Nuesquisser rule actually sort of makes it so what I just did is valid, because they're sort of proving that idea. So in other words, let me just go through it really quickly one time and then just do it the way I did it because it's simpler, okay? So let's make this a little smaller. Okay, here we go. So on the bottom, in order to eliminate this denominator, in order to get rid of it in this complex fraction, we're going to write it, we're going to multiply it by its inverse, so that the denominator, when you multiply it straight across, is just going to be 1. Because everything cancels out, you just end up with a 1 on the bottom. But whatever you do to the bottom, you also have to do it to the top. So let's bring that numerator over, x over y times c over b. Why? Because I'm using the de Nuesquisser rule. If I did it to the bottom, I got to do it to the top, right? Okay, so now we multiply straight across here, straight across here, straight across here, and straight across here. So when you do that, you get xc over yb over, the whole thing over, bc over bc. Now, obviously, bc over bc just simplifies to 1. So then all we have is this thing on top, and that's the answer. So this is all equal to, well, heck, I'll just erase the bottom because that just equals 1. So then this is the answer. Bam. All right. So that they got the same thing that I did by taking this and flipping it and then just doing multiplication straight across. But they sort of showed you how that works because the bottom is going to equal 1 and you're doing the same thing to the top and bottom type of thing. All right, so let's do an example. We can do this. We can do this. Hello there. You know what's funny about that is, to me, it looks like he's saying peekaboo, like he's playing. He's playing. Hello there. All right, here we go. Let's do example 68.1. I'm going to actually get rid of that because it's a little distracting to me. So 68.1, we have this. This is, check it out. I mean, this is the whole numerator, and this is the whole denominator. So we have to do this in 2 steps. And the first step is we have to add the 2 expressions in the numerator, because you've got to make 2 expressions 1. You can't do any sort of division or multiplication just like that, because how do you get the inverse of that? I can't get the inverse of that yet. It's not 1 expression, it's 2. So let's add them together first, and then we can make the reciprocal. Okay, so we're doing example 68.1 here, and the first thing that we have to do is take both of these expressions in the numerator and the denominator down to just 1 expression by performing this operation. Okay, so the top one's going to be easy because as I look at it, I see a denominator here of y and a denominator here of y, so they have common denominators, so I can just do that one pretty easy. On the top, it's going to be x plus 1, and on the bottom is just going to be y. So that's pretty straightforward. I can just do that, no problem. Now, what about the bottom? Oh, actually, the bottom's going to be easy too, because look, they have common denominators too. They made this one easy for us, of course, because it's the first example. So we have a common denominator of y, a common denominator of y. So we're going to do x minus 1 on the top, and then y on the bottom. So now we have to simplify this thing because it's a complex fraction. No one likes fractions on top of fractions. That shouldn't happen. So we're going to use the Dinescu rule, and we're going to end up multiplying straight across, so we only have just 1 fraction. Okay, so what they want us to do here is, I'm just going to erase this part. Okay, I'm just going to erase this part, move this over. So what they want us to do here is they want us to take this bottom part, multiply it by its inverse so that the bottom ends up being just equal to 1. So if I multiply this by its inverse, it's going to be y over x minus 1. Now I do that to the top because you do the same thing to the top and the bottom. And then this whole bottom part, all of this just cancels out. It cancels out because you've got a y here, you've got an x minus 1 here, an x minus 1 here. You can just cancel out that whole thing and it just becomes equal to 1. So that's easy. Now on the top, when you're multiplying 2 fractions together, you can just multiply straight across, right? So on the top, I'm going to have x plus 1 times y. And on the bottom, I'm going to have y times x minus 1. But then, as you see, and they did this step ahead of time, but I don't usually see it like that in my mind ahead of time. So after the fact, you can still do it. So this y cancels out with this y. So what I'm left with is x plus 1 over x minus 1. So I'll write that again. So x plus 1 over x minus 1 because the y's canceled out. Okay, so that's the answer, and that's what they got in the book. Let's do the next example. We're going to do example 68.1. You're probably thinking I'm about as evil as this guy right now, huh? Making you do all of this. Don't worry, it won't be that bad. Okay, I got to get rid of that though because too distracting. 68.1. We're going to simplify this. The first thing, even though it's super tempting to just look at that 7 and just be like, I'm going to get rid of that thing first, that's not the first step. The first step is to deal with, you've got 2 expressions here, you have to add them in order to make it 1 expression before you can do anything else. Okay, so first we're going to add in the numerator. This time, they did not make it easy because this does not have a common denominator. 1 and 1 and 1. Like I can look at this 1 and I could change it to 1 over 1, right? But does that help me? It actually helps me a little bit because the other thing that I can do, that I know that I can do, is I can change that top and the bottom to what? X over x. That's the same as 1. That equals 1, right? And now they have a common denominator. You've got an x and you've got an x. So now I just add straight across. or yeah, the numerator straight across. So that it's going to be x plus 1 on top. And then now that they share a denominator, the denominator stays the same. So x plus 1 over x. And then that whole thing goes over a 7. Okay? So hopefully that makes sense to you. If it doesn't, write a little note to me or text me or something and tell me why it doesn't make sense, okay? Because I want to make sure that you understand this, because you're going to have to know this inside and out before we move on to the next thing. Now, is that a fraction on the bottom? Turns out, yes, it is, because you've got a 7 over 1. So how do we get rid of that 7 on the bottom, because we don't want a fraction on top of a fraction? Well, we multiply the bottom times its inverse. So we're going to do times 1 over 7. Of course, if I do it to the bottom, I've got to do it to the top. Dinescu rule, times 1 over 7. So I multiply the numerator and the denominator by 1 over 7, and let's see what we get. Well, this, if I look at the bottom first, this whole thing cancels out. You've got a 7s that cancel out, 1s that cancel out, and the whole bottom turns out to be just 1. Easy peasy. So I don't even need to write it. Anything over 1, don't even need to write it, right? So this essentially all disappears. Easy. Now I've got this problem. I've got x plus 1 over x. Let me just use a different color so it's clear. Times 1 over 7. Easy. When you multiply fractions, you just multiply the numerator straight across. So x plus 1, and I could be technical and do this, but obviously I don't need to do that because you're just multiplying it by 1. So it's just x plus 1 on top, and then on the bottom is going to be 7x. Let's make sure that I got it right. Yes, I did. That's the same as what they got in the book. So that's the answer, x plus 1 over 7x. Okay, let's move on. Next example, example 68.3. Isn't that a cute little Lego Yoda? Just like waiting for those little snowflakes to fall in his mouth. That's so cute, right? So cute. All right, Mr. Distraction, let's get you out of here though. All righty. Example 68.3. This is on the bottom of page 277. We're going to simplify this. On the numerator, we have 1 over x. On the denominator, we have a rational expression, okay? So 1 minus 1 over x, but we want to change that rational expression so it's not two things, it's one thing. That is step 1. Okay, so the numerator I'm going to ignore for a little while. I'm going to take care of that denominator first. And remember what we did in the last one. 1, what if I make that 1 over 1? That's still 1. What if I make it x over x? That's still 1. Still 1. So I can do that. That is fair game. Totally fair game. Dinescu rule. Why not? I multiplied the same thing by the top and the bottom. So easy peasy. Now, what that allowed me to do is I have common denominators. So I can just add the numerators, which is going to be x minus 1. We're adding by subtracting. And then the bottom is just going to be x. But now I have to take into account this numerator over here. I can't just forget about it. So I have a big divide sign there, and I've got 1 over x on the top. Okay, I'm going to get rid of that equal sign because that's confusing. Now I've got 1 over x divided by x minus 1 over x. I'm just going to do my rule here. Instead of like going through the steps of the Dinescu rule, I'm going to show you my rule one more time. This is Mom's rule. Whenever you divide a fraction divided by a fraction, it's the same as multiplying the top by the inverse of this fraction. So I'm going to just switch that top to bottom. So it's going to be, it's going to be x on the numerator, x minus 1 on the bottom. Easy. Now I just get rid of all of this. Easy. So it's 1 over x times x over x minus 1. And when you multiply fractions, easy peasy, you just multiply straight across. So let's do it. 1 times x on the top is just going to be x. On the bottom, we're going to have x times x minus 1. Now, you could just leave it in that form. Wait a minute. I did something wrong. X times... Oh, I see. No, I didn't do anything wrong. I'm just not done yet. Okay, so this is the correct answer. I did everything right, but check it out. There's something I can cancel. I've got an x on the top and an x on the bottom. Now, it doesn't mean that there's a 0 on top when I cancel those out, right? What it means is there's a 1 on top because that's basically x over x, right? So I've got a 1 on top and just that x minus 1 on the bottom. So this cancels out. Okay, so now that's the answer. All right, easy peasy. Let's do the next example. I know I'm torturing you, but you know these examples get more and more complicated. I know you're probably like, this is madness. Ooh, all right, sorry C-3PO. Let's keep going. Huh, you're impressed I knew that name, huh? All right, we're supposed to simplify this big old monster. Now this big old monster has a double expression on the top and a double expression on the bottom. That's a lot of double expressos. So we need to get rid of those, turn them into 1 by adding. Now, this 1 right here is the key because I can just erase that and make it b over b. Why would I make it b over b? Because that's equivalent to 1, but also it has an added advantage of having common denominators. So I'm just going to do that. Now, what about this bottom one? Let's see. Let me see what we did and add in the denominator. Well, I can just multiply. I can just do the same thing. If I want to have common denominators here, this is going to be the same as 4 over 1. But that doesn't give me a common denominator. So if the whole thing were 1, I would just make it b over b. Why can't I just multiply by b over b? And turns out I can. I can put a b there. I can put a b there. That expression is the same as the number 4. But it gives me an advantage because now I have common denominators there too. So let's add the top now. On the top, I'm going to end up with a plus b over b. On the bottom, I'm going to end up with x plus 4b over b. Now, this is another fraction on top of a fraction, so let's clean up that nonsense. I'm going to move this, okay? And I'm going to move this over, and we're going to clean up this nonsense, okay? So I'm just going to do the Dundas square rule mommy style. Mommy style Dundas square rule is to multiply this by the inverse of that entire denominator. So I'm going to multiply it by b over x plus 4b. And then you can just get rid of this. This just multiplies straight across. Dundas square rule, but mommy style. Now, your book starts canceling things out at this point, which I think that's fine. You can totally do that. So let's look at the things that are going to cancel out. Let me get something nice and bright. How about this orange? That's bright. Okay, so this b cancels out with this b. So when you multiply that straight across, it's like the b's not even there. It's like the b's a 1. Okay, so if I multiply that across, it's going to be a plus b for the numerator, because that's what's coming from here, and this is just crossed out now. And then on the bottom, we're going to have x plus 4b, and I can just ignore this b here because I already canceled them out. Okay, so now the answer is a plus b over x plus 4b, and that's the final answer. Okay, and at least now we don't have fractions on top of fractions. That's why it's simplified. All right, 68.5. Okay, R2-D2. What do you have to say about this? It's hard to know what he's thinking. Get out of here, R2-D2. Okay, example 68.5 says simplify this little bugger. Woo, this is quite the bugger. So the first thing they say, step 1, let's just get rid of all those -1, because what the heck is that all about? I mean, we know that a to the -1 means it's a on the bottom. So that's why, otherwise you could look at this and you could be like, oh, it's not fractions on top of fractions. It's already simplified. But it is fractions on top of fractions because of those -1 exponents. So that -1 exponent means that this a to the -1 times x is basically x over a, right? Same with this one. This b to the -1 times y is the same as y over b. So it was just an illusion that we didn't have fractions on top of fractions, because we still do. And there's one more. this x to the negative 1 is the same as 1 over x. So do you see how I did that? Okay, now it's back to the previous examples, the same level of complexity as the previous examples, right? So we had to do that as step 1, and now we have to take these two expressions, make them one expression by doing this operation. So we need common denominators though. So let's get a common denominator. So in order to make that a common denominator, I'm going to multiply this first one by b over b, this second one by a over a. Now look, common denominators, AB, AB. So when I multiply straight across, I get xb plus ya, yeah, over ab. And then that whole thing is over 1 over x. All right, so now I've still got fractions on top of fractions, so that's not making life any easier, so I've got to deal with that. So I'm going to bring this over. Let's do the je ne square but mommy style again. Mommy style means I'm going to multiply that numerator by the inverse of this. Okay, so times x over 1. And I'm going to write it like that just to prevent confusion, because that is a little, this can get confusing very quickly. So what do we get when we multiply fractions? We just multiply straight across. That x here, I'm just going to put it first and then do xb plus ya. And then on the bottom, I've got ab times 1, but I don't need to write that, obviously. And that's the answer. That is the final answer. All right, so now it's time. Now it's the end. The end. Okay, I'll just show you this little comic. You've got 3 windows here to look at. So in the first one, there's cow yelling car. They all start getting on all fours, eating the grass as the car drives by. The car's gone, and they're back to talking like people. Oh my gosh, that's scary. I wonder if that actually happens. I bet animals do something, like maybe not stand up like that, but maybe they do something when we're around. Who knows what they're doing when we're gone? That is one of those scientific laws that by observing something, you change it, right? All right, anyway, I'll let you go do your homework. Have a great day, Zach. Bye.